Okay, welcome to this module. Yesterday in the last module actually we have recorded few of the equipment, right, how to operate this equipment, and I have shown you the breadboard devices and the details about the equipment, right. So, just quickly let us recall the equipment were DC power supply, frequency generator, we had oscilloscopes, one was CRO, one was digital oscilloscope. In DC power supply we have seen how we can change the voltage, right, and how we can apply plus minus 15 volts if there is a facility within the DC power supply. It was a linear regulated power supply. Then we have seen some discrete components, and finally we have seen a breadboard. So, today's class or this lecture is focused on the application. So, application of what? First we should start understanding what we have learned in the theory class, that is understanding the characteristics of an operational amplifier. So, if you remember in the theory class we have seen several characteristics of an operational amplifier, and the today's class is on how to measure those characteristics. So, let us see what are the characteristics of the operational amplifier, and then when the after one or two slides you will see that once you again refresh what you have been learning in theory, then we will start the experiment. Alright. So, let us see the screen. So, as you see that this particular lecture is focused on experiments on understanding op amp characteristics. So, we will see today what are input bias voltage, input offset current, input offset voltage, input and output voltage range. These are the things that we are focusing today. So, like I said and I have taught you in my theory class, that is what are the operational amplifiers and what are main pins in the operational amplifier. So, if you remember the operational amplifier we have discussed, there are 5 main pins. Of course, there is a 7 pin op amp. It depends on what kind of IC you have. If it is a single op amp or it is a dual op amp or it is a quad op amp. So, we are talking about just a single op amp. If you take a single op amp, then as you see on the screen, there are 7 terminals, 2, 3, 4, 6, 7 which are used, and 1 and 5 are other terminals, 1, 5 and 8 that are used for some other purposes, which we have already discussed. So, let us quickly see the positive supply voltage terminal, that is this one, right, V plus. Then we have second negative supply voltage terminal minus VCC, which is this one. Then we have the output terminal, which is 0.6. Then we have the inverting input terminal number 2, and we had non-inverting input terminal number 3, right. So, this we all remember, correct. Now, the input at the inverting terminals result in opposite polarity. That means that we have seen that if I apply a voltage, right, which let us say this phase, and I say this is 0 degree, if I apply voltage at input 2, that is inverting terminal, what we can see? We can see a voltage at the output with a phase change, right. So, opposite polarity or anti-phase output when you have inverting input at the inverting terminal, right. This we all remember. What was next? The input at non-inverting terminal, that means at terminal 3, if I again apply a signal, right, when I assume that this is a 0 degree phase, then at the output I will have no phase shift. So, what is a no phase shift? It is a 0 degree, right. Again we have seen in the theory class how we can understand what are the phases, right. I have taken the example of a circle, but if you do not remember, let me just quickly tell you how we can measure the phase, or what do you mean by 0 degree, what do you mean by 180 degree, and what do you mean by 360 degree. So, you see, let us assume a circle, and what is, if this is a point, I say this is 0, right. What is this, what is this, what is this, and coming back to the same point, right. See, if I consider this one, this will be 90, right. If I consider this one, this will be 180. If I consider this one, 270. If I consider this one, 360 degree. That means 360 degree and 0 degree is the same thing, is the same thing. That means that if I have a signal here, I see the output here and the signal is applied to terminal number 3, then this is 0 degree phase, this is also 0 degree phase or 360 degree phase shift, it means same thing, right. You say see 0 degree or 360 degree, it is the same thing. So, there is no phase shift. So, we can also say in the output results in the same polarity, right. So, this very easy to understand. So, let us move to the second point, which is the op-amp fabrication. We have also seen in detail how the MOSFET is fabricated, isn't it, and what are the process flow. The op-amp is fabricated on a tiny silicon chip, right, we have seen this, and it is packaged. So, this is a silicon chip, right, we all remember this, and then fine gauge wires are used to connect this chip to the this final terminal pins. These are connecting wires that are connected to the silicon chip, which is connected to the terminal pins, and finally, this whole device is packaged. This is a packaged device, right. So, it is a packaged in a suitable case. Now, why we are kind of repeating this thing, because that I am sure that you are refreshing your lecture notes, but if you do not remember or you have forgot something, it is easy to see in this particular lecture what things we have already studied. So, let us go to the next slide. Now, this is the same thing that we were discussing, that if I apply a voltage at the input, right, and the output will be 180 degree phase shift, which is my if it is a non-inverting terminal, this is non-inverting terminal, right, signal is applied to the non-inverting terminal, then my signal is like this, output is also similar, which you see here, which is without any phase shift. But if I apply my input signal to the inverting terminal, my output would be 180 degree phase shift. So, this we have already discussed in last slide. Op-amp is a very high gain amplifier fabricated on an integrated circuit, right, that we know, combination of many transistors, FET resistor in a pin side pin head size space. Now, we also know that recently when we talk about op-amps, it has billions of transistors, but all are MOSFETs, right, very few or almost none uses the BJT technology anymore. Most of the op-amps you will see the circuit within it would be of a MOSFET. MOSFET is nothing but metal oxide semiconductor field effect transistors. So, that is why we are saying as many transistors including FETs resistors. It finds application, again if you remember what are the application, audio amplifier, signal generators, signal filters, right. It is also used in biomedical instrumentation and numerous other application. Now, what are the advantages of op-amp? We already know, right, the advantages of op-amps are it is low cost, right, less power consumption, more compact, more reliable, high gain and easy design. So, this we know. How it is related to our today's experiment? Today's experiment is on understanding the characteristics of op-amp. So, what are the characteristics, a few of the characteristics of an ideal operation amplifier? When we say ideal, that means that everything that we think, right, is there. For example, if you take a ideal person would not have any kind of negative things, right, is a godly. So, same thing when you talk about ideal op-amp, it would have infinite voltage gain, it will have infinite input impedance, it would have 0 output impedance, it will have infinite fast. But we rarely find a person who has who is ideal, right. Same way we cannot not also find operation amplifier or IC which is ideal. So, we cannot have the characteristics that we really want in an operation amplifier, but we will have a practical operation amplifier with some characteristics which are not really ideal, but close to ideal. Okay. So, what are those characteristics? Like I said, if you take a ideal operation amplifier, then you have infinite voltage gain, we will see, but practical operation amplifier it would be somewhere around this value. Input impedance is infinite. So, we understand what is input impedance, right, and we will see the input impedance of an practical op-amp is around 10 to the power 12 ohms, 0 output impedance, but in true the output impedance is not 0, it is low. then we have infinitely fast, that means that it is super fast, but it is not possible. We will see slew rate in this particular experiment and we will understand and measure this slew rate, and we will see it is somewhere falling between 0.5 and 20 volts per microsecond. So, these are the ideal characteristics of an ideal operation amplifier, but we are not going to use an ideal operation amplifier because we do not have ideal operation amplifier. So, what we have? We have a practical op amp, we have IC that I have already shown it to you in the lecture notes. Now, we have also seen two golden rules, is not it. So, first is the input to the op amp draw or source no current, that means that the input terminals will draw or source no current, there will be no current drawn from the input terminals, that is first rule. Second is the op amp will do whatever it can to make the voltage difference between the inputs 0. This is also we have studied in detail right in lecture notes, that these are the two golden rules that we have to remember, that one is the inputs draw or source no current, and second the voltage difference between two input is 0. So, I am sure all of us remember this thing, right. If you do not remember, do not worry, that is why I am kind of repeating the things that you have already been studying in the theory class. Let us see the op amp characteristics. So, these are the several characteristics of an operation amplifier. This is an op amp like we see here, right. We have seen the IC from 1 which is offset null, right, 2 inverting, 3 non inverting VEE, right, 8 is not connected. Now, the question to you guys is, what is the role of pin number 8, right. If it is NC, that is not connected, right, but what is the role, why it is there, if it is it useful or what is the purpose. So, that is the kind of question for you. So, find it out what is the role of pin number 8, alright. Then we have pin number 7 for plus VCC, 6 for output, 5 for offset null. This everything we have seen in the theory class, right, what is the role of each pin. So, today we will check several things in the experiment, starting with the input impedance, output impedance, input bias current, input offset current, input offset voltage, slew rate, common mode rejection ratio, common mode input voltage. So, several things are there, right. If you see, the first one that we will be discussing is the input impedance. Input impedance would be extremely high in case of ideal operation amplifier, or in case of or you can say its input impedance is infinitely high. But if you take a operation amplifier which is a practical op amp, right, which is right in my hand here, that we have seen yesterday, or I can keep it here so that it can be focused easily, right, this one, then we will see it as a extremely high input impedance. Same way the output impedance for ideal op amp would be 0, but if you see in the practical operation amplifier, this operation amplifier, then you will see that the output op amp is not 0, but close to 0, alright. Then we will see infinite gain, in this practical operation amplifier the gain will not be infinite, that we will see today. So, let us see one by one, alright, let us see one by one. The first one, that is your input impedance. So, what is input impedance and what kind of input impedance are there? First one is your differential input impedance. What is differential input impedance? Differential input impedance is total resistance between inverting and non-inverting terminal. That means, what is the difference? What is the difference between inverting and non-inverting terminal? That will be your differential input impedance. What is a common mode input impedance? Common input impedance is nothing but total resistance between each input and ground. That means, the resistance between this and ground, or between non-inverting terminal and ground, the resistance between it. So, what is the resistance between this and ground? What is the resistance between this terminal and ground, right, this terminal and this terminal, or this terminal and ground. So, that will be your common mode input impedance. One is your differential input impedance, another one is your common mode input impedance, alright. So, remember these terms. If you see this circuit, we have taken this circuit from electronic tutorials. We have, if you see here, there is a signal Vs, right, then the resistance is because of the source. So, Vs is a source, so resistance is Rs. This is the input impedance of the amplifier Zin. So, if you draw equivalent circuit, we will have Rs and Zin in series. If you want to measure the voltage V in this terminal which you see here, then what formula you have? You have formula which is V in V in equals to what? This is Z in or Z in upon R s or divided by R s plus Z in into your source voltage V s. This is V s, right. So, this is what is the formula for your equivalent circuit which we have written here, alright. Now, this is very easy because this is nothing but a potential divider, voltage divider circuit. So, when you want to measure a voltage across Z in, you have Z in R s plus Z in into V s, it is very easy, right. So, now let us see the output impedance. Input impedance we have seen. Now, let us see the next slide. Let me just remove these things. Okay. So, we go to the next slide. What is the next slide? The next slide is a output impedance. So, if you again see output impedance ideally it should be 0, right. We have seen ideally it should be 0. Resistance viewed from the output terminal to the operation amplifier, that is resistance from the output terminal of the operation amplifier. In reality it is non-zero, or extremely small, So, this is an equivalent circuit for measuring the output impedance. You can clearly see there is a signal generator, the amplifier, and there is the oscilloscope or voltmeter. Same way we will see today there is a signal generator nothing but a function generator. We have seen in the last modules what is function generator, right. Then we have seen what is oscilloscope, or we have also seen how we can measure the AC voltage, right. So, depending on the load, if we vary the load we will see the change in the signal at the output of the operation amplifier. So, this is about the output impedance. Now, let us go to the next slide, which is the effect of bias current. Now, we have already seen the effect of bias current, or what is the bias current and how it can be used, right. So, again this circuit is taken from allaboutcircuits.com, this particular circuit that you see here, right. So, let us consider the effect of bias currents. If you could take a non-inverting amplifier, non-inverting unity gain amplifier, we have seen what is unity gain amplifier in the lecture notes, right, driven from a source impedance of 1 megohm. If IB is 10 nanoampere, it will introduce an additional 10 millivolts of error. It is very easy to understand this thing, as this degree of error is not trivial in any system. So, this is first point. Now, bias current is a problem of the operation amplifier because it flows in external impedances and produces voltage which adds to system error. To reduce the system error the bias current, when it flows in the external impedances, right, it produces voltage, that means it will cause an error. So, how we can reduce this error? So, it is very important terminology to understand what is a bias current, alright. So, if the designer simply forgets about IB, if the circuit designer forgets about the IB and uses just a capacitive coupling, the circuit will not work properly, right. So, we will see in detail what exactly this bias current and what are the input offset current, input bias current, and so on and so forth in the following slides. Let us see. First is input bias current. Okay. So, you understand this circuit, right, understand this, look at this circuit in detail. Now, let us see what is it. For ideal operation amplifier, we know, right, there are golden rules. The golden rule is that no current flows into the input terminals, no current flows into the input terminals, right. We know this. For the practical operation amplifiers, right, op amps, AOPAMPS, there is a mistake here, op amps, the input currents are very small, of order of 10⁻⁶ to 10⁻⁴ ampere. Most of the operation amplifier use differential amplifier as the input voltage. The two transistor of the differential amplifier must be biased correctly, but practically it is not possible to exact matching of two transistors. So, what does it say, right, what does it say? Let us see again. The practical op amps have input currents which are extremely small, order of -6 -14 ampere, right. However, most of the op amps uses the differential amplifier. So, if you are using differential amplifier, the two transistors in the differential amplifier should be matching. If they do not match, then there will be some change in the output, right. So, if the transistors are not matching, it does not match, then we cannot bias the transistors or differential amplifier correctly. So, for what to do that? So, we cannot do anything regarding the matching of the two transistors, but there is another way or another solution to do that is the input terminals which are the base terminals of two transistors do not current small DC. This small base currents of transistor are nothing but the bias currents IB1 and IB2. What I said, see the input terminals which are the base terminals of two transistors. So, when we see a differential amplifier or op amp and differential amplifier, within the op amp there are transistors, and these transistors conduct the current, a small DC current which are the base currents or through the base terminals of the transistors, and these small base currents are nothing but we call them as a input bias current, or we can say IB1 and IB2. Why IB1 and IB2? Because it is a differential amplifier. We have two different transistors in the differential amplifier. Now, thus how you can define input bias current? Input bias current can be defined as the current flowing into each of the two input terminals, when they are biased at the same voltage level when the op amp is balanced. That means that when you balance your operational amplifier, right, when you balance your amplifier, then you will find that there is a small amount of current flowing into the two input terminals. That small amount of current, when you have biased your op amp, right, when you have balanced your op amp, not biased, balanced your op amp, then the small amount of current that you find, right, flowing into the input terminals is called the input bias current. But sometimes it is difficult to understand until we really perform the experiment. So, we will see the experiment of how we can calculate the input bias current, alright. The two bias currents are never same, hence the manufacturer specifies the average input bias current, right, which can be found by adding the magnitudes of IB1 and IB2 and dividing by sum of 2. So, let us quickly see what is the input bias current once again. Input bias current, like we say, is due to non matching of two transistors 1. Now, the two bias currents that we get are never same, right. That is why when we get the operational amplifier, the manufacturers already give us the formula of finding the input bias current. How? By adding the magnitudes of IB1, IB2 and dividing the sum by 2. This is the formula that you have to remember when you take an example of an input bias current, right. So, easy to remember. Now, if I say input bias current, then we have input offset current as well. So, before we go to input offset current, let us see the input bias current in terms of the experiment, alright. So, we will start with input bias current, we will go to another characteristics in a short while, but let us first now complete the experiment for input bias current. So, I will request my teaching assistant, you already know him, Sitaram, who was with us in the last lectures, right. So, can you please come and connect the circuit. So, now we focus how he is connecting the operational amplifier with the things that we have on the table, which is our, if you remember what is this? This is your function generator, this is your DC supply, right, linear DC regulator supply, and this is your oscilloscope, digital oscilloscope. So, he will be connecting the breadboard along with the operation amplifier and resistors like you have seen in the slide. So, if you quickly see the slide, these are the resistors, is not it, 1 and 2, right. So, we are going to perform the experiment to understand what is the input bias current for the operation amplifier, that is 741. So, I am sure that he is using 741, alright. So, let us see how to connect this particular circuit and how to measure the characteristics, okay, alright. So, let us see this particular slide first by the time he prepares the circuit, and then we go on the circuit. So, the slide shows input bias and offset current. We will just consider right now input bias current, then we will see what is input offset current, and then we will come back to the table, alright. So, here we have to measure input bias current, right. So, this is experiment for input bias current. So, what is the table shown here? So, let us see here, connect the circuit as shown in figure. This figure is already shown, you have to connect the circuit exactly like a figure. So, if you are somewhere in your university, right, where you have a op amp and if you have the resistors with a DC power supply, then you can perform this experiment quickly, right. You just need a multimeter, you just need a DC power supply and then you can measure this input bias current quickly, right. You can also do it at home. This is very easy experiment, it does not really require a high end technology or extraordinary facility. This experiment we can do even at home, alright. So, what is that? Use a digital multimeter, measure the DC voltage at inverting terminal and record the values in the table. That means that we have to measure the voltage at inverting terminal and we have to record the value. How? So, one is at inverting terminal, one is at non inverting terminal. You see DC voltage, if you see this table, if you see the table, DC voltage at the non inverting terminal V plus, we have to measure the DC voltage at non inverting terminal, we put the value here, DC voltage inverting terminal, measure here and put the value here. Then we can have IB plus is nothing but this V plus divided by 220 K, IB minus is V minus, right. So, here will be V plus, here will be V minus. So, V minus, right, divide by 220 K, that will be your IB plus and IB minus. We already know the input bias current formula, input bias current is IB equals to mode of IB plus IB minus divided by 2, right. So, we will see this experiment, let us see the same circuit he has attached and I will show it to you how he has attached on the breadboard and then we come back to the screen, alright. So, let us see the circuit. Yeah. So, if you see here, right, what you see, you have applied here, where are the bias voltage? Bias voltage is here. So, you see the red pin and black pin in the center, red pin, right, and a green pin, right, this way green pin. These are plus minus 15 voltage, plus minus 15 volts given to the operation amplifier. Operation amplifier is right over here in the center, right, is in the center. Then we have connected two resistors. Can you see two resistors? We have connected two resistors, right. Yes. So, these two resistors are the resistors connected to inverting and non inverting terminal of the operation amplifier, correct. Then we have to now measure the voltage at the inverting terminal and then we have to measure the voltage at the non inverting terminal, alright. So, what is the voltage at inverting terminal? Let us see what is the voltage at non inverting terminal. If I have a multimeter, yesterday we all know, right, we can use a multimeter and we keep the multimeter at the DC voltage. Now, let us see what voltage we get at the inverting terminal. So, now you have to understand, when you take an operation amplifier, I will show it to you here, there is a small dot, you see. So, guys, when you see close, you will see a dot which is here, right here. This is pin number 1, it is easy to understand, which is pin number 1, alright, and which is pin number 8. So, pin number 1, 2, 3, 4, 5, 6, 7, 8. So, in that particular sense, when we connect the IC to the breadboard, we know what is pin number 1, what is pin number 2, alright. So, he has connected, now let us focus on the breadboard. He has connected the integrated circuit which is 741, right, with the resistors at the input terminal, inverting terminal and non inverting terminal. Now, we are measuring the voltage at inverting terminal, then we will measure the voltage at non inverting terminal. So, let us first see voltage at non inverting terminal, voltage at the inverting terminal. Point 1, right, 0.1 millivolts, 0.1 millivolts. Let us see at non inverting terminal, 0.1 millivolts, 0, it is 0, okay, good, alright. So, we have two values, right, we have two values. So, let us go back to the screen, Now, what we measure at inverting terminal? 0.1 1 millivolts, at non-inverting terminal 0 millivolts, right. From there we can put this equation I b plus, right, V plus is 0 divided by 220 k, right, which is equals to 0. Then I b minus equals to 0.1 millivolts by 220 k, right. So, we will get another value here, then we put the value of I b plus I b minus divided by 2, that will be your input bias current. You got it. Again you concentrate on this table, once again let us see what we have found. We have found the current or the voltage at the first we have connected this circuit. This circuit was there on the breadboard, where you have seen 220 k resistors connected to the inverting and non-inverting terminal. Then we have applied plus VCC, right, and minus VCC or VEE to the pin number 7 and 4, right. Then we have grounded this resistor. Now we have measured the voltage as non-inverting terminal, we have measured the voltage at inverting terminal. So, from here we can write whatever the voltage we measured in this column at non-inverting terminal, whatever voltage we have measured here in the terminal which is inverting, then we can put this voltage in this particular equation, which is your I b plus. From there you will get your value of I b plus, right. Let us say the value is x. Then from this voltage which is inverting terminal you get I b minus, which is equals to, let us say, y. So, what will be your I b? Input bias current is I b equals to x plus y by 2, we can write mode, right. This is how we can measure the input bias current. So easy, extremely easy, is not it. So, now in the next module let us see how we can measure the input offset current, alright. Let us see input offset current. Okay. So, we stop here.